Afternoon, sir.
All right, hope you had a good week. Let's see how we can kick this off as quickly as possible. The first thing is, some people want to come in. First thing is that I have posted, I think, 3 videos which I'm hopeful were helpful. And it's on that premise that I will try and ensure that whatever you need to understand based on the syllabus, and that's the only thing that I've gotten so far, that we're able to successfully navigate through this course. So my question has started, how many people got a chance to actually watch videos, Z Transform in particular?
Hi.
Okay. All right, I'm seeing a few hands raised, but I was hoping that I've heard everybody saying that they have watched the video, and there would be no ready for participation on such discussion. All right, so from the video, from those who watch and are from reading, can anybody basically, let me just bring up something here, 1 second. Yeah, can anybody, just give me in a brief way, what is your understanding of the Z transform? Still there? No one?
All right. I guess my liquor understanding is it will be the equivalent of the Laplace transform of the discrete time. So it's a way of representing discrete time signals in the frequency domain. Something like that. Something like that.
What else?
Basically the same things there. Yeah, basically the same thing. We know that. Yeah. Well, I don't really know how to put it into words, but basically what he said, the rundown of it.
Okay, because when I think
that there's a range as well, a particular range that determines system stability as well. I believe, and you prefer your system to be stable more than anything else, more than causal.
Okay. All right, so that's the first thing we have to start in terms of, some form of understanding of what the whole concept of the Z transform is. So let's or is it that I'm starting at a point where, again, my apologies because I'm still trying to get Mr. McLeavy for some clarity or clarification.
Sound like a lesson in futility.
So I would define the Z transform as a process of converts a discrete time signal, which is a sequence of real and complex numbers into complex frequency domain representation. So again, the Z transform converts discrete time signal. And last week I elaborated a little on what is the discrete time signal and frequency or continuous time signal, which is in frequency. So it's converting the discrete time signal, which can be real or complex numbers, into a complex frequency representation. It's considered similar to a discrete time equivalent of a Laplace transform form. Anybody here would not understand basic Laplace transform? Okay. All right. So what you saw in the video basically is an explanation initially of the Z transform, the equations that you use to represent systems to do the conversion, and it speaks to the fact that you can actually represent signals in a better way as compared to Laplace transform, which are some signals you are undefined and cannot be represented. But the Z transform can actually represent some of those signals that seem to be have a challenge in being represented in the Laplace transform format. Now, well, at least let me not go through that. Let me find out again from you, because probably again, just give me a raise a hand for those who have actually listen and watch the video. Where am I? Where am I now? So from 26 people, we have only 8 people who have raised their hands. watch the video?
No, sir. About 12 or 11 or 12 did raise them, man. Some did just put it down immediately after raising. I was watching. But yeah.
So if we're not able to watch the video, how are we going to be understanding or even trying to attempt to understand what's there?
Sir, we will catch it, sir. Just, I think you have the ability to break it down for us, and I think we'll get it.
There's another approach. You can lower your hands. Doesn't mean the less than 50% of those who are here have watched the video. Okay, let's do this.
In this form, okay?
Are you guys seeing my screen?
So, yes, sir.
Yes, sir.
What are you seeing now?
The YouTube video.
Okay.
Pause the YouTube video.
Okay, good.
What I want to talk about today is the Z transform.
I'm gonna since you guys are here and some haven't watched it, we're gonna go through it. We're gonna just tell me where you are that you're not understanding, and I'll stop to do a brief breakdown or explanation. Because if you don't watch this is my notes that I brought to you. If you don't watch it, then I don't know what to explain apart from just going on the board, writing stuff, which again, you probably don't understand. I'm trying to find the easiest method and a way to communicate, a discussion type of way to communicate in the shortest period of time that we have, and not necessarily to be flooding you with information as in notes, but something that actually makes some sense. I've gone through it. I've edited the video. I've gone through what I think is probably the best way. All right, so we're gonna go through. I'll be here. I'll be watching and listening. Just let me know, sir. Whatever. All right. How about that? One thing that I want you to do in the interim,
Yes, sir.
ladies and gentlemen, is not just only to just be there watching. I want you to grab your notepad. I want you to grab your pen. I want you to grab something that you can actually follow and make some scribblings or some notes while you're going through. Questions, then you ask them as we go along. All right?
Sir,
Yes, sir.
sir, from the video. So the context it was to use Z transform to find region of convergence and the poles and zeros to draw a pole zero diagram. Is that what we are going to be focusing on also?
Yeah, that's it. If you look at the syllabus, that's pretty much understanding the Z transform to find what is called a region of conversion and to see how some systems are stable and what make them stable and what the system, why you're unable to find the regions of conversion for some systems. Understanding the process, and then after doing the video, as I said to you before, I'm going to give you guys some tutorial aspect questions that you can actually use to see how you can transfer the information that you have learned into real practice questions to solve problems. All right?
Yes, sir.
All right, let's go.
And so, kind of as a setup, right? What we talked about so far was kind of in a continuous world and the discrete world. And we started talking about the continuous time Fourier transform, right? So in the continuous time world, I define this integral over some continuous time sigma dt, right? And so I call this the continuous time Fourier transform.
Sir, mute one of the devices.
We have
There's an echo.
the discrete time Fourier.
What was that, Chad?
So I was asking if you could mute one of your devices because there's an echo.
Okay.
Transform, which is,
Sir, there's someone waiting to be let in.
instead of an integral, it's a sum. So since I have a discrete set of x values, that means I turn this infinite integral into an infinite sum, and it looks kind of similar otherwise, right? We define this as the discrete time Fourier transform. Now, when you were taking signal systems and differential equations, you also saw the Laplace transform, right? So Laplace transform, which I'm not going to talk about really at all in this class, I'm just putting this down here as a reminder of what you hopefully remember. The Laplace transform was kind of like a generalization of the Fourier transform, right? What I was doing was I was replacing j omega with this more generic complex variable s, right? And so the reason that we cared about the Laplace transform was that it allowed us to solve problems that we couldn't solve with the Fourier transform alone, right? And so in some sense, you know, once you know the Laplace transform, you can solve a lot of things in the Laplace domain without actually having to be going back to the Fourier transform. The advantage of the Fourier transform is that it has this very intuitive and concrete interpretation as frequency. We know a lot of real-world electrical engineering systems involve frequency, and so that's why, you know, we kind of need them both. And so the question today is, what is the discrete time version of the Laplace transform? And that's what's called the Z transform. And again, the idea is the same. I turn this infinite integral into an infinite sum, and I replace the e to the j omega n with a z to the minus n. Okay? And so, again, this is a more generic idea, where before my omega was only a kind of real valued frequency variable. Now z is some complex number. And so let's pause and ask, so why do we, you know, why does this make sense as a thing that we want to do to a signal? Okay? And so, again, one of the things that we showed for both the continuous and discrete time Fourier transforms was that these exponentials, e to the somethings, were kind of important for LTI systems in the sense that when e to the something went in, the same e to the something came out, just modulated by this frequency response, right? And so the same thing is actually true for z's, right? So kind of remember that if I had something like, you know, e to the j omega 0 n, and I put that into the system, what came out was basically the frequency response like so. So in the same way, z to the n, more generically, is special for discrete time LTI systems. What do I mean by that? Well, let's suppose that my input signal is this z to the n. So I usually try to put a little bar through the z if I forget, you know, you should keep in mind this is a z and not a 2, right? So this is going to be z to the n for some complex z, okay? So what is the output if I put that signal through an LTI system? Okay, well, it is going to be my usual convolution between whatever my impulse response is and whatever my signal is. And I'm going to plug in what I know here. I have the impulse response, and I have x to the n minus x of n minus k is the same as z to the n minus k. Since this sum is over k, I can take the z out, and I have just the sum. And this, in fact, is the Z transform of the, well, so basically this is what we call the Z transform of the impulse response, right? This is called the transfer function. And what we showed is that if this complex exponential comes into the system, what comes out is the very same complex exponential just multiplied by, again, this transfer function evaluated at complex number Z, okay? And so what we've just kind of shown here is that this notion of special signal comes in exactly the same as special signal comes out, just modulated by some complex number. That's exactly true. Even so, what we kind of showed before was this was true for some specific set of complex numbers. That is, the ones that are on the unit circle, e to the j omega something. But here, this is actually true for any complex number. Okay, and that's why we can talk about more generic transformations than just the frequency response. So, just as a refresher, so let's look at the relationship between the Z transform and the Dtft. So the Z transform is the following. It's this sum x of n z to the minus n, and the Dtft is this sum x of n e to the minus j omega n. And I can see that these formulas look pretty similar. In fact, this is exactly what I would get if I took x of z and I evaluated it at the points z equals e to the j omega, right? What that means is that that's like saying that if the Fourier transform, the Dtft, exists, what it is the places where z, the complex number z, is e to the j omega for some omega. And so that means that in my z-plane, if this is the real part of z and this is the imaginary part of z, the Fourier transform is exactly those places where that complex number happens to be on this unit circle, right? So this sketch is z equals e to the j omega. And so kind of what we're saying here is that when the Fourier transform exists, and I'm going to talk about this concept in more detail in this lecture, because one thing that you should remember about the Z transform that may be familiar from Laplace is that the Z transform has what's called a region of convergence, right? This formula, this function x of z, isn't automatically defined for any z that you choose. It's only certain z's that make this formula converge. And so when the Z transform and the Fourier transform both exist on the unit circle, then they're related by this thing. And so this actually makes it kind of clear that since I'm evaluating omegas as they go from 0 to pi, this kind of makes it clear that the Dtft has to be periodic, because so this, again, as a reminder, the Dtft is 2 pi periodic. So I'm not going to talk about Laplace too much, other than to say that just in the same way that the j omega axis, the imaginary axis, played a big role in analyzing continuous time systems, the unit circle plays a big role in analyzing discrete time systems. Okay, so I'm going to say unit circle is key for discrete time systems like the j omega axis was for continuous time systems. Right, so if you're doing a continuous time class, you spend a lot of time worrying about, when did poles, for example, cross over the j omega axis that affected the system's stability and so on. We're going to talk about exactly the same concepts here, except now we care about when do poles stay inside the unit circle, right? So there's kind of a symmetry here, there's kind of a relationship here. Okay, so okay, so I'm going to pause and ask for a second. Does that make sense? Any questions?
right. So as the gentleman says, so far, we have any questions?
Well, sir, I was just trying to put together the connections of how the relationship between the Laplace, how I was using the Laplace to compare to the Z transform. I didn't really get that so clearly with him using the unit circle explanation.
Well, the unit circle basically is important in the Z transform because it tells you where you're. All right, just like for Laplace transform, you remember I talk about omega?
Yes, sir.
All right, so omega, with your 2 pi, you have your different region. Omega is just like your circle, right? But it's just that it's an angular frequency. Now, the unit circle in Z transform is that area that tells you where the signal actually is, where the function exists, whether or not it is actually inside a circle, on the circle, outside of the circle, and that by extension is going to go. The circle is going to be one of the demarcation point that helps you to understand what the whole concept of what they talk about, region of conversion. Right, so it's just to say that Laplace transform, we use omega, and Z transform we use in the unit circle. So just like how we'd have, a signal pi over 2 or pi over 4.
Or you're expecting a particular,
expecting a particular function.
Yeah, right. Okay.
Right?
Yes, sir. So like real and distinct roots, stuff like that. In that case.
That's correct.
Okay, I understood. That's a bit clear.
All right. So we're going back to the video. So I'm gonna mute this.
All right, sir. Thanks again.
Okay. So why do we need this Z transform? So why do we need the Z transform? Well, one reason is that the Dtft doesn't always converge or exist. Right? So we showed last time that kind of a sufficient condition was that if I were to sum up these things, I would get some non-infinity number, right? That's like saying that, I need to be able to sum up the absolute values of the signal for that sum to converge, right? And we talked about how we could relax this slightly, but for the moment, let's just assume this is the condition that we need for the Dtft to exist in the way that we want it to. By that I mean I want to make sure that as I take incremental approximations to the Dtft given by increasing n from 0 to infinity, that I want to make sure that my Dtft converges at every point of the signal to the actual Fourier transform value, right? I want to avoid these Gibbs phenomenon kinds of issues, right? And so not every signal satisfies this constraint, right? And so if we're staying in Fourier transform world, we kind of have to throw up our hands at this point and say, well, there's some signals that I can't analyze with the Fourier transform, right? Because the Fourier transform doesn't exist. The Z transform allows us to talk about a more general class of signals, okay? And so some points to remember are, the Z transform may converge in places where the Fourier transform doesn't exist. So that's one important reason. One other reason, which is not really the best reason in the world, but it's good to keep in mind, is that the notation is generally easier, right? So, we get a lot of polynomials in Z, or we get rational functions of Z. So in general, you kind of lose all these e to the j omega things that were a little bit kind of tedious to kind of keep in mind. And, like when we were doing the homework on the Dtft, right, you see you have to keep track of all these e to the j omegas, and it's kind of a pain, right? Whereas z's are much cleaner, just like manipulating polynomials. And the third one is that the Z transform helps a lot when designing filters. We're going to talk more about that after the first exam, but the idea is that, I look at what are called the poles and the zeros of the Z transform, and understanding what those poles and zeros are doing helps me extremely in terms of designing filters that do what I want to do, right? It's tough to design filters directly in the frequency domain, but it's a lot easier to do it in the Z world, okay? So let me drill down a little bit into this first point about when the Z transform converges, okay? And the critical concept here is called the region of convergence. Which we sometimes call the ROC. Okay, so again, this all kind of follows way back when from sums and series in calculus, okay? So I'm not really telling you anything that you couldn't have done in theory in high school, almost, or first semester of your freshman year. So here's the idea. Let's write Z in polar form, some magnitude e to the j theta, or actually maybe I should say r e to the j omega. We always use omega here. And so now let's say, okay, let's look at the Z transform in terms of writing Z in this way. Okay, well, it's, here's the regular Z transform, Z to the minus n. If I plug in really being explicit about Z, I'm going to write this like r to the minus n, e to the minus j omega n. And if I look at this, if I kind of draw parentheses around here, this is like saying, this is like the Dtft of some kind of modified signal, right? So in some sense, what I'm saying is, I'm taking the Dtft of the original signal kind of modified by this r to the minus n. And so, the way I think about this is the Z transform converges if I have the same condition that I had here before. And so here, this is kind of making it clear that the Z transform may converge in places where the Fourier transform doesn't, right? So if r equals 1, and this convergence thing at the bottom is true, then the Dtft exists, and the Z transform also has a region of convergence that includes r equals 1. But it's also possible that for changing this value of r, it may be true that r equals 1 does not satisfy this criterion, but if I were to crank up r, basically, if I were to, dampen down the original signal by multiplying it by some decreasing exponential, maybe I could get the sum to converge, and the Z transform would exist for that certain value of r, right? So what I'm kind of doing is I'm looking to see what is the range of r for which this sum converges. Okay, and so just to make an example, so let's consider the step function, okay? So the step function, certainly, if I were to look at this sum, right? Well, I would get infinity, right? Because I'd be adding up, all those numbers. So I can't take the Fourier transform of the step function, right? Not possible to do. However, if I were to look at u of n r to the minus n for some real r, well, in that case, the sum would look like this. And I would kind of get out the step function like this. And here I would say, okay, well, this would be equal to, 1 over 1 minus r if this magnitude was greater than 1. Right? Because what I need to do is, a different way of looking at this is this, right? I could also write it like this. Hopefully that makes it a little bit more obvious. When I have an infinite series like this, I need to make sure that each of these terms, right, is less than 1. And so this is going to converge in this region, right? And so if I was going to say, the ROC of the Z transform of U of n is the magnitude of r greater than 1. And the way I draw that is like so. So I draw a unit circle here, and then I kind of draw this sunburst that says that any z that I pick out here will satisfy this constraint, and therefore this sum will converge, and then I can talk about the Z transform in this region. Anywhere in here, I can't talk about, right? Because the radius is less than 1, and this sum will just blow up. Right? So, again, this is a signal that I can analyze with the Z transform in certain regions of the complex plane that I can't analyze with the Fourier transform, right? So, and here you can see, question.
Is this supposed to equal 1 over 1 minus 1 over r instead of 1 over 1 minus r? The summation form.
Oh yes, this should be like this, right?
Yeah.
Yeah, sorry about that. Yeah, that was a little bit too quick. So that's the same as this, right? Yeah, you're right. Good point. Sorry about that. Other comments or questions? So you can see here that because everything here depends on R, my regions of convergence always involve circles in some sense. Circles in the complex plane that are centered at the origin. So a different way to say this is that, convergence of the Z transform depends only on the magnitude of Z, which I was calling R in the previous slide. So that means that regions of convergence look like things that only depend on the radius. So I could have a region of convergence that looks like this. The one I showed you in the previous example looks like everything outside of a circle. I could even have something like this, where I have things that are between two circles. And so, I mean, in some sense, these guys here, are actually kind of like special cases of this guy here, right? So if I were to take, this guy and say, okay, now I'm going to let the outer circle go out to infinity, I get a picture that looks like this sunburst. If I take this guy and I say I'm going to take the inner circle and bring it down to 0, then I get this circle, right? So I mean, in some sense, ROCs generally look like this, something like, the magnitude of values like this. And, it's possible that if I were to take in the limit, this is like saying I have the absolute value of Z less than something, and it's like saying the absolute value of Z is greater than something. Okay. And so, as I mentioned, kind of to motivate this, when the ROC includes the unit circle, that means I can talk about both the Z transform and the Fourier transform. So if the ROC includes the circle, then the Dtft exists, which is a way of saying that that Dtft sum converges. Okay. And so this convergence of the Dtft has a special name, okay? And that's called stability. So if the Z transform of an impulse response H of n for an LTI system converges on the unit circle, which is another way of saying that the Dtft exists, then the system is stable. So we're going to talk a lot more about stability and what it means in future lectures. For right now, this is more of a definition than anything else, right? Just saying that, you know, we call the system stable if it has a Fourier transform, okay? And in some sense, the stability of the system means the system is doing good things. It means that if I put some arbitrary input in the system, it can't do crazy things that produce some output that explodes out to infinity, right? It kind of means that the system is, in general, well-behaved. I'll talk about kind of more what that means in just a second, or in a few lectures maybe.
All right, so you guys would have done control systems, signals and systems. When we talk about a system being stable, remind me in general term, what does that mean for the system?
So ask a question there again, repeat it.
From controllers, systems. When you talk about a system being stable, what does that mean?
It's not oscillating. And it has negative complex poles.
So here, we're talking about the Z transform being defined in a specific way, show you that the system is stable. And once the system is stable, remember, again, only thing I want you guys to understand, because sometimes people get caught up so much thinking about the equations and all that, that you miss the concept. The main concept is that you're applying an input signal to a system. The system, based on its transfer function, will give you a particular output. And sometimes the output is desirous and can be controlled. Sometimes the system output is just morphing into something that is unusable. So we're looking at a system, we're using Z transform, no, because we're moving from discrete time to some form of frequency. We're looking at a complex system or complex numbers, right? So as you know, the system can be complex, the system can be complex, the system can be stable, the system can be provided with a particular gain. So all the Z transform is doing is looking at a LTI system that would not necessarily be represented well using Fourier transform, because there are some things that the Fourier transform will not be able to give you. So, in a nutshell, that is what the lecture is. It's just that it's showing you some further steps, all right?
Yes, sir.
Okay. And so, okay. So, as we're going to see, I'm just going to make a note of it now, that a lot of times we can write the Z transform as some numerator over some denominator, where these are both polynomials in Z. And some of the examples that we're going to do next are going to be in this form, okay? And so there are kind of two interesting things, right? One is that when the numerator is 0, that means that the Z transform is 0, and these are naturally called zeros of the transfer function. And when the denominator is 0, that means that this thing blows up to infinity, and we call these poles. And so there are important connections between the zeros and the poles of the polynomials and the ROC of the Z transform. So we're going to talk about that in a moment here. But as you'll see, especially when we come to filter design, a lot of filter design is all about understanding where the zeros and the poles of the transfer function are in order to make the filter do what I want it to do. So let's do an example of a exponential sequence. So what I'm going to call this is a right-sided exponential. A to the n u of n. And so it's called right-sided because it only starts at 0 and then it goes on to infinity off to the right-hand side, right? And so when a, or when the magnitude of a is less than 1, I get kind of a decreasing exponential. When the magnitude of a is greater than 1, I get an increasing exponential. And so you can kind of already predict that the ROC has to do with when a is less than 1, right? Because otherwise, I'm never going to get sums that converge with pictures that look like this. So let's actually compute the Z transform. X of n, z to the minus n. In this case, this turns into, from n equals 0 to infinity, a to the n, z to the minus n, which is a different way of looking at it as a over z to the n, right? And so what I need here is, so this will converge if, I guess I should say it this way, if this absolute value here is less than 1, right? We know that from our infinite sum formula, which is a different way of saying that the magnitude of z must be greater than the magnitude of a. And if that's true, then the value it actually converges to is this 1 over 1 minus a over z, which is, if I multiply by z all the way through, like this. And now here I can draw what's called the pole zero diagram, which means that I can make a plot of saying, okay, there's only one place where the Z transform is 0, that's at Z equals 0, and I draw this circle here to indicate a 0, and I draw an X to indicate a pole. And so I have a pole over here at A. Here in general, A could be some complex number. I'm drawing it right now as if it's a positive number, but in general it looks like this. And then my ROC is going to be a circle like this, and everything outside of that circle is going to be in the ROC. So I can see here that if A is strictly less than 1, then the ROC includes the unit circle because that sunburst is going out beyond the unit circle and the Fourier transform exists. Otherwise, the Fourier transform doesn't converge, right? And so we already kind of saw that when you were doing the Dtft, that I could only look at the Dtft of signals where this number was like a quarter or a third or a half, right? I couldn't do this with A being 2, otherwise the Fourier transform wouldn't exist, right? Okay. So questions or comments about this? So I showed you a right side exponential. Let's talk about a left side exponential, right? So a left side exponential is kind of the opposite, where I'm going to define this guy. Now this may give you a pause for a second about how do we draw this, right? So first of all, let's think about this, right? So when n equals 0, I get u of minus 1, right? Step function at minus 1, that's 0. When n equals 1, I get step function at minus 2, right, which is also 0. So basically any n greater than or equal to 0, the number inside these brackets is going to be negative and I'm not going to get any contribution. Whereas when n is minus 1, I'm going to get u of 1 minus 1 is 0. That's the first time the step function turns on, right? When I have u of minus 4, for example, I'm going to have u of 4 minus 1 is 3, so step function will also be on there. So this is a function that basically, is on from minus infinity to minus 1, and that turns off at 0. And so, again, I'm going to get functions that look kind of like, depending on the size, it could look like something that's decreasing like this, or it could look something that's increasing like that. And so let's compute the z transform. So my x of z is going to be this sum, x of n, z to the minus n. And now I'm going to say, okay, well, this thing, because I know that this is a step function that only turns on this way, it's going to look like this. And I'm going to have minus a over z to the n. And now I'm going to just kind of relabel what I call n, right? So instead of going from minus infinity to minus 1, I'm going to just flip this. And now I'm going to have I'm going to have z over a to the n power. And now, this is something that almost looks like a sum I can do, right? So what I want to do is I'm going to say, well, first of all, again, when does this sum converge? So this converges if the absolute value of z over a is less than 1, right? I need to have each of these terms getting smaller and smaller. And then what is the actual value of the sum? Well, it's like 1 over 1. Again, here, I've got a negative sign that comes out this way, so it's like this, minus this. And I have to subtract off, actually, that includes a minus 1 that I don't, make sure I do this right. Yeah, this includes a minus 1 that I have to add back in, right? Because normally the sum formula goes from n equals 0 to infinity. And so if I write this out, what I have is minus a over a minus z plus a minus z over a minus z. And what I get is minus z over a minus z, which is the same thing as z over z minus a. And so here's a part where I stop and say, well, wait a second. This is actually the very same z transform that I got last time. right? So if I look back at my other example, right, I ended up with the Z transform being Z over Z minus A, right? So that seems wrong, right? It seems like I shouldn't be able to get two discrete time signals that have the same Z transform. But the key idea here is that they don't have the same Z transform because the Z transform comes in two parts, both this function of Z and the region of convergence. And here, the region of convergence is actually opposite of what we got last time. Last time, we got the region of convergence being Z outside of this circle. Here, the region of convergence is Z inside of the circle. And so, basically, the ROC here looks like, again, I have a 0 and a pole, and this time the ROC is inside the circle. So the key idea is that Z transform consists of both an algebraic form of x of z that says where this is valid. Right? So the conclusion is that I can't just tell you, hey, the Z transform of a signal is blah, you know, this function of Z, compute the inverse Z transform. The reason I can't do that is because I need to tell you what is the ROC in order to disambiguate which of the possible time domain signals I might mean. Okay? So that's why you always have to make sure that you note the ROC when you're working on a problem like this. Otherwise, it can get confused. Now, it's fair to say that in a lot of the problems that we do, we're going to deal with right-sided signals. And so maybe what I may say in some future problems is something like, you know, here is this function of Z, you know, and it's a right-sided signal, right? As you'll see, that pins down what the ROC is. And so that means I don't necessarily have to tell you exactly what the ROC is. I just have to tell you, am I looking for a right-sided signal or a left-sided signal? And that distinguishes between this and the sunburst pattern. Okay. Okay. So questions or comments? So let's do a little more complicated example. So here I'm going to kind of just use the linearity of the Z transform. So here, let's suppose that I have this signal. Okay, and so again, just like with the Fourier transforms, after you've kind of learned what a property is, I'm going to allow you to use it. You know, this is not about just grinding through, you know, algebra. So here we can immediately conclude that this signal has a Z transform of Z over Z minus a half, with the ROC being the absolute value of Z greater than half, right? That's kind of what we've learned just before. This guy has the ROC Z over Z plus a third, and the ROC here is going to be Z greater than a third. Okay, and so now I have to think about, okay, well, the Z transform is going to be the sum of these things, whatever it is, and so I can just kind of compute stuff out. I'm going to get a Z minus a half over a Z plus a third in the denominator, and in the numerator, I'm going to get whatever this turns out to be. So I guess I'm going to get a 2Z squared minus a half of Z plus a third of Z is going to be minus a sixth of Z. And so if I factor out the Z, I get 2Z, Z minus 1/12. Okay. So I figured out what the, I figured out what the algebraic form is. Now, what is the ROC, right? So for the ROC, I need to have both of these things existing at the same time, right? Or in the same place. So I have to draw my two ROCs, right? I have, this is a third and this is a half, right? So one of the ROCs looks like this, and one of the ROCs looks like this. And so if I look at the union of these two things, right? So what I do is I look at, or actually I'm sorry, I look at the intersection of these two things. These things both have to happen at the same time. And so looking at this guy over here is the one that's more restrictive, right? So the final ROC looks like a starburst that's outside of a half. And this intersection is this guy. And so again, if I were to draw the pole zero diagram, what I would get would be the following. So I guess I didn't leave myself that much space, but I guess I could try and do it over here. Right, so I have a 0 over here at 0. I have a 0 at 1/12. I have a pole at a half, and I have a pole at minus a third. And then my ROC looks like a circle that extends out from a half. And so, as you can see here, somehow the ROC is related to the poles, right? And we're going to see that more generally. So the zeros don't really play any role in what the ROC could be, but the poles are what play a huge role, right? Because I need to look at the things that involve the denominator. And just to illustrate the point that, again, just as I had in the previous example, a right-sided thing and a left-sided thing that gave me the same algebraic form of z, but different z transforms, I can construct a signal that also does the same thing here. So I'm not going to work out all the algebra, but if I consider this signal kind of has a part that is right-sided, and it has a part that is left-sided. So that's like saying this part covers what's happening for n greater than 0, or greater than or equals 0. This covers what's happening when n is less than 0. And it turns out that I can work this out to this very same algebraic version. But the ROC is different, right? Because the ROC for this guy is, again, the absolute value of z greater than a third. The ROC for this guy is the absolute value of z less than a half. And I can look at the intersection of those things. So here, one of the ROCs looks like this. And the other ROC looks like this. And so if I look at the intersection between those two guys, then I get this kind of a ring, where I have a third and a half, and the intersection of those two things is all the stuff that's inside this ring shape, okay? And so again, even though I have very much the same pole zero diagram, here, I get a very different ROC, right? And in fact, if I wanted to, I could consider a purely left-handed signal that had, again, the same algebraic thing and the same pole zero plot, but the ROC would be basically just inside this circle here. So fundamentally, there are actually three possibilities for valid Z transforms that have the same pole zero plot, okay? Okay, so like I said, I'm not gonna drive you crazy with lots of left-handed and double-sided signals. I mean, most of the stuff we do in this class is still going to be assuming that things start at 0. And one of the reasons for that is that, again, most of the time, the signals that we care about are impulse responses. And for impulse responses to correspond to causal systems, I have signals that are right-sided, right? I don't want to have impulse responses for which h of n is 0 or is non-zero for values of n less than 0, right? So I kind of want to make sure that my impulse responses are all right-sided. That means that, I'm going to get nice kind of ROCs, they're always like these sunbursts going out. Okay. So, comments or questions? Okay, so let's do a slightly trickier one. So, what if we have a finite length exponential? So everything I've done so far has been some signal that extends to infinity in one direction or the other, or both. But what about something like this? So here, oops, sorry, let me just redo this picture here. So here, what I wanted to do was something like this. This equals a to the n for n within this range, and 0 otherwise. So what that looks like is just something that turns on at 0, it exponentiates for a while, and then it turns off at some point, and then at 0 afterwards. So there's only a finite number of non-zero elements. And so what is my x of z going to be? Well, I'm going to have this guy, a to the n, z to the n, or z to the minus n, right? So here I've kind of just noticed that this sum can only be non-zero in these places. And again, this kind of looks similar to what I had before, except now I'm going to say, well, I can write the answer, which is going to be 1 minus this thing to the n power over 1 minus this thing. You know, this is going to be true no matter the value of a, right? The reason is that the finite sum formula is valid. This formula is valid no matter what the value of this is, because there's only a finite number of terms in this sum. So there's only a finite number of terms. The formula is always valid. And so if I kind of multiply everything through by a z to the n power, what I can get here is I have z to the n minus a to the n over z to the n minus a z to the n minus 1, which is a different way of saying z to the n minus a to the n over z to the n minus 1, z minus a. And so here, I would take a look at this and say, okay, well, again, now I have a polynomial in z over polynomial in z. So I'm going to have capital N zeros, which are the zeros of this top polynomial, and capital N zeros, which are the zeros of this bottom polynomial. Okay? So my pole zero plot is going to be a little more complicated. So I have to ask myself, okay, I'm going to get, let's look at the poles first. So I'm going to get n minus 1 poles at z equals 0, right? Accounting for this. And I'm going to get a pole at z equals a. And here, I'm going to get n poles, or I'm sorry, n zeros at the complex roots right? So here, I've got a complex number to the n power equals this number here. And so this may be something that is not familiar to you, but, you know, the nth roots of some number are generally distributed around the unit circle like so. So here, say I have n roots, so say I have n equals 8. What that means is that I'm going to have a pattern of things that look like this. Kind of evenly spaced around the circle. This is going to be like absolute value of A. This is going to be a minus absolute value of A. This is going to be the absolute value of AJ. This is going to be minus absolute value of AJ. And these guys are going to be like, you know, square root of 2 over 2 plus square root of 2 over 2J times absolute value of A. So just there are going to be 8 complex numbers that give me the zeros of that top polynomial that are generally evenly spaced around the circle. And then my poles, I'm going to have basically a whole bunch of poles at 0. I'm going to have, let's say, 7 poles, if n equals 8. And I'm going to get a pole, as we talked about, at z equals a. Right? I have this extra pole here. And so here I see that this location has both a pole and a 0 on it. And so these things are basically going to cancel each other out, right? So there's not going to be a 0 here or a pole here because the numerator and the denominator both kind of cancel each other out. Those terms vanish. And so actually what I have is 7 poles at the origin and 7 zeros scattered around the complex plane. And one thing to observe here is that, you know, the ROC is any value of z that is not 0, right? And so that means that fundamentally any value of z, I can look at the z transform for this signal. And so this is generally true when my input signal is only finite length, right? So the problems come in when the input signal is infinitely long. In that case, I have to think about things like convergence and sums. But the intuition is that if I have only a finite number of terms to add up, nothing can ever go wrong unless I'm adding up kind of infinity plus infinity all the way through, right? So here, this is an illustration of, you know, finite length input means that ROC is the whole z-plane, except possibly z equals 0. So, in some sense, when I have a finite length input or a finite length impulse response, life is always pretty good, right? There's no need to worry about poles because all the poles are clustered together. Okay, so we're going to talk, you know, more about pole zero patterns in later lectures. Okay, so comments or questions about this example? Okay, so let's make it a little more complicated. So what about this signal? 2 to the n cosine 3n u of n. All right, so this looks a little more complicated. But again, the first step is always to remember that whenever you see a cosine or a sine, you can turn it into an exponential, right? Because a cosine is like the sum of 2 exponentials over 2. And so I can immediately say this is like 2 to the n e to the j 3n plus e to the minus j 3n over 2 un. And so I can immediately kind of say this is like 1/2 times 2 e to the 3j to the n plus 2 e to the minus 3j to the n u of n. And now each of these terms is in the form of, you know, something to the n times a step function, which I already did in the previous problem, right? So my x of z, I can immediately conclude is 1/2 times, well, what was my formula? It was like saying 1 over 1 minus 2 e to the 3j over z. Oops, plus 1/2 1 over 1 minus 2 e to the minus 3j over z. Right, all I'm doing is applying this formula right here, right? So I got a to the n u of n. Nothing here says that a has to be a real number, right? A can be any complex number, and my z transform is 1 over 1 minus a over z. That's exactly what I have, 1 over 1 minus the a, which is this, over z. Okay. And Now, what is this thing going to turn into? Well, I'm going to have to multiply through by some stuff. So I'm going to multiply each of these guys by a z. And now I'm going to multiply through to get a common denominator. So I'm going to get z minus 2 to the minus j plus z minus 2e to the plus 3j over the product of these things. So I'm going to get 2z squared minus, well, let's think about this for a second. So what I'm going to have is, I'm going to have a z, or I guess a 2z, times e to the minus 3j plus e to the minus 3j, or I'm sorry, minus plus, right? So again, here I'm going to get my cosine coming back at me. And the same thing here, I'm going to get z squared minus 2z, this thing, plus 4, and then when I multiply these things together, they cancel each other out. So what I'm going to have is 2z squared minus, this thing is like 2 cosine of 3j, so I'm going to get 4 cosine of 3z over, I think I lost a 2, there was a 1/2 floating around there, so there's a 2 times all this stuff. So then I'm going to get a 2 times z squared minus 4 cosine of 3z plus 4. And so then I'm going to be able to cancel this 2 out to get z squared minus 2 cosine of 3z over z squared minus 4 cosine of 3z plus 4. Okay, so I kind of came up with the algebraic part of the z-transform. And now let's think about what does the ROC of this thing have to be. Okay, so actually before I do that, let me just think about this, the poles and the zeros. So what do I have here? Well, I actually kind of can read off from the here before I multiply things out. I get the poles at z equals 2e to the plus or minus 3j. And here I can see what the zeros are. I get zeros at z equals 0 and z equals 2 cosine of 3. Okay, so let's think about what the ROC is for a second. So again, let's go back to this formula here, right? The only time that I can do this is when the magnitude of each of these terms is less than 1, right? So the ROC of, the ROC for this was magnitude of z greater than a, right? So in this case, a is going to be like, what was it? It was like 2e to the plus or minus 3j, right? This is just some complex number that has magnitude 1, right? So the magnitude of this thing is just going to be 2. And so if I were to draw the final thing, my ROC would be this. I can draw what my poles and zeros where I'm going to get a pole. So here's a circle of radius 2, right? So this is like a circle of radius 2. I'm going to get poles at these locations here, where this angle is basically, 3. So I get poles at 2e to the plus or minus 3j. And I'm going to get zeros at basically this location and this location. And my ROC looks like this. I guess if I was being more careful, these poles are actually probably over here because 3 is pretty close to pi. So forgive my poor diagram, but something like this, right? In fact, let me just draw that better. So probably the ROC is more like this. So this is pi, right? So my poles are probably over here, right? I have a 0 here, and I have a 0 here. But the ROC is still looking like this. Okay. So at this point, what we should notice, right, is that the ROC always looks like it's somehow related to the poles. And so let me just make some statements about how the ROC and the poles are related. So kind of rules about the ROC. So number one is that the ROC is a ring or disk centered at the origin. We kind of already showed why that was true, because it depends only on the radius of the complex variable, and so that means that it's got to be something that only looks like a circle or something. So the ROC contains no poles, right? And that's kind of by definition, right? Because if the Z transform is infinity, right, that's what a pole means, then certainly it doesn't converge there, right? So the Z transform never contains any poles by definition. Or I'm sorry, the ROC never contains any poles by definition. 3, we kind of showed earlier, is that if x of n is finite length, the ROC is the entire z-plane, except possibly you may run into problems at exactly 0 or exactly infinity. So basically, if kind of I have a couple of caveats, so or a couple of cases, right? So if x of n is left-sided, my ROC is basically going to be the region inside the innermost pole. So if I have a bunch of poles out here, the ROC is going to be this region like this, the region inside all the poles. If I have a right-sided signal, the ROC is going to be kind of the reverse. It's going to be the region that is outside the outermost pole. And if I have a kind of a two-sided signal, then the ROC is generally going to look like some sort of a donut that is defined by the ring between two poles. So I could have more poles out here, I could have more poles inside, but in general, it's bounded by the poles. So this is kind of a way of saying the ROC is always bounded by the poles, and then in special cases, I kind of know that a left-sided signal looks like this, the right-sided signal looks like that. In this case, there are many possible donut-shaped ROCs that correspond to different, two-sided signals, and I have to kind of disambiguate within there which one I meant. Okay. So one thing that I can't have is, right, I can't have a pole in the ROC, right? That's rule number 2. And I guess the final thing I want to say is that so the ROC kind of tells us is the system stable? So ROC meaning for a transfer function h of z. So when I apply this to a linear system, I can say, is the system stable? And is the system causal? So stable implies that the ROC includes the unit circle, and causal implies that, you know, the impulse response is right-sided. And so that means that I can have some cases where I can say, okay, you know, I can just kind of look at some possible ROCs and say, here's the unit circle in each case. Right, so these guys are the unit circle. And let's suppose I have poles at, you know, 1/2 and -2. So there are 3 different kinds of ROCs I could have here, right? One is this guy. One is this guy. And one is kind of this guy. Right? So this one here, sorry for my crappy drawing. So this one here includes the unit circle. So this is a stable system. But because the ROC doesn't go out to infinity, this is not causal. Here, this guy looks like a right-sided signal, so this is causal. But since it doesn't include the unit circle, it's not stable. And this guy neither includes the unit circle nor goes out to infinity, so this is not stable, and it's also not causal. And so the thing that we desire the most is a system where all the poles are inside the unit circle, and the ROC looks like a starburst going outside that pole, the outermost pole. So the best case scenario, maybe this is a little bit slangy, let's say most desirable scenario. Number 1 is that ROC looks like, here's the unit circle. All the poles are inside the unit circle. And the ROC looks like a ring that is, or it looks like a sunburst that is extending outside the outermost pole. Right, so the idea is this is the unit circle, i.e. ROC extends outwards from the largest magnitude pole and all poles are inside the unit circle. Right, so when we design systems, especially things like control systems, this is what we want, is we want to kind of make sure that all the poles are inside the unit circle and that the ROC extends beyond the outermost pole, right? And this is exactly analogous to stuff that you must have done in signals where we wanted, for example, to push all the poles into the left half plane, right? That meant good things for continuous time systems, right? And just in the same way that there were tests to show whether or not for a given Laplace transform version of the transfer function the poles were in the right place, there are similar things for discrete time, right? So all those things like the Routh-Hurwitz test and root locus and stuff like that, you can do that for discrete time too. I don't think I'm going to get to things like root locus for this, but the same ideas apply. And that stuff is actually kind of fun, like drawing the little diagrams for when things go past the unit circle. I always like that stuff, but I don't think we're going to do it in this class. Okay, so all I talked about this time was basically the forward definition of the Z-transform. So what I'm going to talk about next time is kind of how do we deal with inverse Z-transforms and what are some Z-transform properties that make our life easier. So any questions or comments? Okay. In that case, we are done for the day.
Okay. As the gentleman say, any questions or comment?
So it's a lot to take in one time, so.
And that is the reason I wanted you guys to do it. This thing has been up a couple of days, well now, more than a week for sure. And I wanted people to take your time because pretty much what I'm going to be doing is the same thing, unless I'm going to be teaching. Anything I'll be doing is the very same thing. It's actually, I found it very simple with examples. I'm going to give you some examples right now that follows to help to try and concretize what was shown. There's a reverse side, as I mentioned before. It's the inverse Z-transform, just like we have the inverse Laplace transform. And that is if you want to go from the frequency back to the discrete time domain, how do you do that? Again, using Z-transform. But as it relates specifically to the lecture, any questions? I mean, I know it's a lot to take in, but are there any place? And this was one of the things that I had mentioned before. Watch the video, make your questions, make things that you would found to be challenging, and let's see if we could have them. No questions? No concerns? Okay. Are you seeing my screen now?
Yes, sir.
Again, just a few examples.
Let's actually work through a set of examples, or we'll actually get some practice at evaluating the Z-transform. So first, let's do Z-transform example 1. So in this example, we are going to find the Z-transform signal x of k equals.
Oh, that's because I need to close my mic.
This signal. So we're going to start off simple. We're going to start off with this signal that is equal to 1 at time minus 1, 3 at time equals 0, 2 at time equal 1, and a negative 1 at time k equal 2, and it's 0 everywhere else. So if I was going to plot this signal in discrete time k, it would end up looking like this. It's equal to 1 at minus 1, it's equal to 3 at time 0, 2 at time 1, and a negative 1 at time 2, and it is 0 everywhere else. What I am asked to do in this problem is I'm asked to compute the Z-transform of this signal. This is actually what we call a finite length signal, so we're actually not going to have to worry about any convergence issues here, because when we evaluate the Z-transform, there won't be an infinite number of things I'm summing up. There's only going to be 4 things that I'm summing up, because there are only 4 non-zero samples in this signal. So this is kind of a good first one to work on, because in terms of region of convergence, it's a much simpler type of problem to work. So let's go ahead and compute the Z-transform. By definition, the Z-transform is the sum from k equals minus infinity to infinity of our signal times z to the minus k. Well, for our particular signal here, almost all of the terms in this infinite sum are 0. The only terms that aren't 0 is at k equals negative 1, k equals 0, k equals 1, and k equals 2. So I can actually simplify my limits quite a bit. from k equals minus 1 to 2. I haven't changed anything because for our particular example, I just have zeros outside of here, but this simplifies the limits quite a bit. And now, since it's such a short list of things, I'm actually going to write out each term. So at k equals minus 1, my signal x of k is equal to 1, and I have to multiply that times z to the negative k, where k is equal to minus 1, plus the k equals 0 term, I'll have x of 0, which is 3, times z to the 0, because k is 0, plus the z equals 1 term, or k equals 1 term, x of 1 is equal to 2, so I have 2 times z to the negative 1, because k is 1. And then finally, the last term is when k is equal to 2. I'll have x of 2, which is a negative 1, times z to the negative 2, because k is 2. So what I end up with is just z to the 1, plus 3, plus 2z to the negative 1, minus z to the negative 2. So this is the z transform of my discrete time signal x of k. It's a polynomial in z, and this is the z transform of the signal. One other
Give me a hands up for those who understood that one. You realize that it's not far-fetched from what was done in the lecture, right?
Yes, sir.
Here it speaks to the fact that it's a finite, and he also defined in the lecture that once it's a finite system, that is when z is actually greater than 0. It's a finite system. You have no issues with finding things like the conversion, right? And you can see why. Because for a finite system, it means that and I hope that it's making some sense now. We're seeing that we have a discrete signal. So the discrete signal was what was issued, or was given rather. And you need to find the Z transform of the discrete signal. You see why it's a discrete signal? I alluded to this last week that at time interval 1, the signal amplitude is checked when it was analog, and then you can get a discrete value for that signal, specific value at each time interval. So here, based on the time intervals that were given in terms of k, you have specific values for the signal. And then you're to find the Z transform of this discrete function. Very simple. Normally the expression, so there are a couple of things that you need to know right off the bat. You need to know the expression, general expression for the Z transform. And here, of course, it goes from minus infinity to infinity in terms of the time. So pretty much it goes on and on and on. But what you want to do is to find specifically the Z transform within a certain time boundary. And this is what was done for this very first one. Thank you, Sean. You can lower your hand. All right, let's look at the second example.
Sir,
Yes.
one moment, please, sir. If you realize he has a positive 2, but down in the calculation he has a negative 2. It should have been a negative 2 up at where k is.
Let me revisit it. Sorry, let me go back. All right, so I'm looking on it now. What was that?
There probably is me overlooking something because I was asking about the positive 2 and the negative 2.
You mean for the expression here?
Yeah.
All right, so what we're doing is simple, and you can always work it out again on your own. But what we're doing is this is a general expression for the Z transform, transforming the function x of k, and k is with regards to time, right? K is a time interval. So you want to take it from a time interval to the Z transform. So it becomes x of z, which is expressed generally as this expression. Whatever the function is, yeah, z to the minus that time interval. And in this case, because you're given the time intervals, and it says otherwise or elsewhere, the function is 0, he basically shows what that meant. And so the amplitude or the magnitude of the signal at the different intervals of time. And what he did was, of course, gave the general summation, he wrote the summation that goes from time minus 1, so from here to here. So you transform it to the Z transform minus t. So this, what is the first one? The amplitude is 1, and you do the Z transform, which is minus 1, which is minus, and the time interval is minus 1 here. And that's where you get it. So minus and minus give plus, right? And z to the 1 is z, and times the magnitude. What's the magnitude? 1 plus, I will do the same thing here. The magnitude of the function, in this case, at 0 times 0 is 3. So I have a 3 here. Z to the z, well, minus, but it's minus 0. When it's minus or plus 0, any variable raised to the 0 power is
1.
1. So that's what I get the 3 here, okay? And then second one here, this one here, the magnitude again at time, at 1, time being 1, is 2. So we put a 2 here, times z to the minus 1, z to the minus 1. So 2 times z to the minus 1 is 2 times z to the minus 1. And then it has the amplitude here is minus 1. See it here, down here, at time 2. T at time 2. So I have minus 1 as the amplitude, z to the time, which is minus 2. So this become a minus, so you have a minus here, and z to the minus 2. So what was the question, Miss?
Sir, it was a mistake on my part. Sir, I was looking at the k, but the k is actually to the minus. So whatever k is up at the top where the quadrant are, sir, the minus.
Is that Miss Henry? That's Miss Henry?
Yes, sir.
Okay, you weren't coming in so clear, so I wasn't sure.
Sir, I was saying.
Right. No, I hear you, but I wasn't hearing you clearly, so I could not clearly distinguish that it was your voice. But I got you.
Okay.
All right, so let's move on to the next one. All right, so let me mute my mic again before I start with the echo.
Another thing I'll do right now is I'm going to find the Dtft of the signal. We've talked about how easy that is to do if you already know the Z transform of the signal x of k. And we already do know that the Z transform. It's right here. We can get the Dtft out of this Z transform just by evaluating it on the unit circle. So what does it mean to evaluate on the unit circle? It means pick the points that are unit magnitude away from the origin. Well, that is the set of points z equals e to the j omega, because e to the j omega is the unit circle. As omega changes from 0 to 2 pi, it maps out a circle in the complex plane. So I can get out x of omega by simply replacing every z in this equation by e to the j omega. So that's what I'm going to do. I replace the first z with e to the j omega, plus 3, there aren't any z's there to worry about, plus 2 times z to the minus 1, but z to the minus 1 is e to the minus j omega once I've swapped out z with e to the j omega, minus e to the minus 2 j omega. So I can easily get out the Dtft of my signal just by evaluating the z transform on the unit circle. For this case, we didn't have to worry about the region of convergence containing the unit circle, because for finite length signal, the only places that we have to worry about are when z is equal to 0. You can see that this thing actually blows up. If z equals 0, I'd have 1 over 0. So the only point that we have to worry about is z equals 0, or when z is infinity or minus infinity, if I plug into x of z, it blows up. But those are the only points you worry about for finite length signal, the origin and infinity. So those are the only points that aren't contained in the region of convergence. So the region of convergence does contain the set of points on the unit circle. So we're free to plug into x of z. And once we plug into x of z, e to the j omega, that gives us the Dtft of our signal. So this is a nice, short, simple example, a finite length signal where we compute the z transform. And then once we compute the z transform, we also get out the Dtft almost trivially by just plugging in z equals e to the j omega.
Struggling with math?
All right, any question on that one?
No, sir. Seems that straightforward.
Okay. Now what I want you guys to do for me now, with the I will answer you, sir, in another forum. What I want you to do for me now is, again, to take the lecture. So you have in your own time, you have examples. I'm going to also supply a couple more examples so that you can actually start to see a little bit more. I'm going to put some examples where we have to be considering the ROC because of the function, and to see how it is that we overcome such challenge. All right. Somebody said that it was much, but I'm sure that the much is not so much, because if it took you, this is our 10th week, and it took you so much time to actually go through certain things. I don't know how, in the name of Jesus. I don't know, unless you guys had challenges with Mr. McLeave in terms of understanding the math that was aligned to it. But I'm not sure exactly what was happening, why it took so long. What I'm going to be doing, I've also posted, ladies and gentlemen, two other things to do specifically with the same Dtft versus continuous time. Again, which would be an earlier part of the notes based on what you said that you have not covered, so that it can hopefully help you in terms of provide a better understanding of what's happening. Am I clear?
Yes, sir.
See my screen again?
Yes, sir.
Yes, sir.
One or two more problems. I'm gonna allow it to soak. And I will take you guys again when you're a little, fresh in terms of moving through the different component of the course. Don't worry too much, Mr. about exam. What I'm more importantly interested in is whether or not you're understanding the concept and you can actually engage problems that come your way. And the exam will be no different, all right?
Yes, sir.
Number 2. This example is a little bit more complicated than the first example we worked because this is a signal that has an infinite number of non-zero samples. So the signal we're going to deal with here is x of k equals alpha to the k times the unit step u of k. And we are going to find the z transform and region of convergence for this signal. Remember what the region of convergence is. This is a region where the z transform exists. So ROC is what we mean by region of convergence. So let's start by just writing down the definition of the z transform. X of z is a sum from k equals minus infinity to infinity of x of k times z to the minus k. That's just the definition of the z transform. And then we can go ahead and plug in the specifics for our problem. K equals minus infinity to infinity, alpha to the k u of k times z to the minus k. And then since the unit step is 0 for all negative time, it turns on at k equals 0, we can let the unit step manipulate the limits of the sum and simplify this to k equals 0 to infinity of alpha to the k, z to the minus k. So now this is the summation that we need to solve. And we know how to work on things like this. We've been doing things similar to this in the class for some time. If we use our property of exponents, we can rewrite this as alpha to the z to the minus 1, all of that raised to the k. That's equivalent to that last step. And now this is in a form that we know how to just write down because we know how to solve a geometric sum. If I want to, instead of writing alpha to the z, alpha times z to the minus 1, I could write this as alpha over z. And this might be a little easier way to write it because now I know to think about the relationship between alpha and z in terms of whether this sum converges or not. Because that's something we would have to worry about. If this quantity being raised to the k is magnitude larger than 1, this sum blows up. We need the quantity alpha over z's magnitude to be less than 1 for this to actually have a closed form solution. So when we write it in this way, it's kind of easy to check whether this actually converges or not. And it converges as long as that quantity is less than 1. If we multiply both sides by magnitude z, we can rewrite this as magnitude of alpha is less than z, which is the same thing as magnitude z being greater than alpha. So this right here is the criteria for this geometric sum to converge. This converges anytime the magnitude of z is larger than the magnitude of alpha. So going forward now, when we actually write down the answer for this sum, this quantity right here is what we're assuming is true because it's only under this case that the geometric sum actually exists. So if this is the case, we can actually just use our table and we can write down 1 minus the quantity raised to the upper counter variable plus 1, which would be 1 minus alpha over z to the infinity, and then divided by 1 minus alpha over z. Since we're going to assume that alpha over z's magnitude is less than 1, this simplifies into 1 minus 0 because alpha over z to the infinity is 0. And then on the denominator, I wrote it as 1 minus alpha z inverse. If you wanted to, you can multiply top and bottom by z. So this would turn into z over z minus alpha. So whether you like this form or this form, they're totally equivalent, but sometimes different textbooks write the answer in either this form or this form. So what we've done is we have solved for x of z. We have found that x of z is equal to z over z minus alpha for all values of z whose magnitude is greater than the magnitude of a. So there is our answer. That's our z transform, and this quantity here is the region of convergence. I can actually plot that region of convergence in the complex plane, or the z-plane, however you want to say it. Let's say that alpha, for now, is just a real valued quantity, so it's on the real axis. All the values of z whose magnitude is larger than alpha is the shaded region right here. All these points that I've shaded in orange are outside the circle that has a radius of alpha. So all of these points in the z-plane are the points whose magnitude is larger than the magnitude of alpha. So this is what the region of convergence looks like for this particular problem. This right here, that point alpha, that's what we would call a pole of x of z, if indeed alpha was a real value to alpha. In general, this quantity alpha could be anywhere on this circle if we wanted to deal with a complex value to alpha. But in general, the spots where x of z blows up, and in this case, it's when z equals alpha, because over here on the denominator, if I plug in z equals alpha, it blows up. That's what we call a pole of the transform. It's a spot where x of z equals infinity. So that wraps up this example. Starting with a discrete time signal x of k, we have computed its z transform, we've found the region of convergence, we have sketched the region of convergence, and we've identified the pole of x of z, which is a spot in the z-plane where x of z equals infinity.
Excuse me, sir.
Yes.
Question about the region of convergence. Just for clarity, yes, what you're saying is that whatever is inside the unit, the circle, the unit circle, that does not exist for the discrete time, is what you're saying, and we're trying to use z transformation to help to show these times.
That's correct.
Okay.
That's absolutely correct.
Okay, because I got a bit confused trying to understand the whole unit circle, and I realized I really have to go back over. Naturally, I also have to go back over what we just did with trying to determine where the region of convergence is, because I'm having a little bit of difficulties in understanding that part of the lecture that we went through. So
okay, no problem. I'll also provide more clarity since you said that you're having issues. Well, it's really it's not difficult at all. What happened is that there are certain places that you have region of conversion. For example, in the last example I will look at.
Yes, sir.
Remember what Z is? Z is a complex quantity.
Yes.
Right? It's a complex quantity that basically could be anywhere.
Right.
The unit circle gives a demarcation point as to whether or not Z is that complex. Well, first of all, the unit circle gives an expression for Z equals to e to the j omega, right? Well, which really tells you that, okay, at this point, you can have a complex number anywhere on this unit circle, that the magnitude is 1, but a complex number, 1 raised to a complex variable that goes different parts. So it could be 1 minus 1, but it goes at different parts along the circle. The region of conversion really speaks to the fact that if the value of this complex number is, well, I should probably back up. So you remember how you get to poles and zeros, right? Do you recall how you get the poles and zeros from transfer function?
Yes, sir.
Okay. So from the transfer function, we can get zeros and we can get poles. Remember, the poles are the numerator and the zeros are the denominator of a transfer function, right?
Yes, sir.
Okay. And again, based on the complexity of the expression, you can have one pole, 1, 0, or many, because it all depends on whether or not it's a quadratic expression or a complex expression, right?
Yes, that's correct.
Right. So what will happen is you want to see where a region of conversion, the poles are usually on anywhere along or in on the unit circles guided to help to guide you to where the poles are. It's best when the poles are at, well, I won't say best. It's best for a transfer function based on the gain that you want if your poles are at zeros, meaning physical zero, right? Because it made the expression simple, and you can then work the transfer function or work the gain of the system. But the problem is when the system is complex and you can't find your poles on zero, and by extension, a transfer function becomes complex, it means that you have to find some way of finding whether or not your system is stable. Remember, we talk about the system whether it's stable or not stable?
Yes, sir.
And a stable system is a system that you want to work with, because an unstable system means that at one instant your gain is going to be at a certain value, another instant your gain is going to be at, you put in the same quantity but you get a different gain, so it becomes unstable. And again, you go back to things like your control system and you learn about from there your overshoot and underdamping conditions, right?
Yes, sir.
But you want your gain to be stable. So you want to find something that converges to give you, in a particular region, to give you a stable gain. And be that as it may, it is important to make a determination if your function that you have, one, it is, you can find a region of conversion, which then tells you whether or not your system is stable or not. And that's pretty much what you're looking for with all of these expressions. And there are certain guides that tell you what tells you whether or not you have regions of conversion. So, for example, show you that the magnitude of Z must be greater than the magnitude of the amplitude of the expression that you're trying to find. Otherwise, the amplitude of the expression is going to be all over the place, which makes your system unstable. And that's all they're trying to do. Find if your system is stable or unstable. And that is done basically using the region of conversion.
Yes, sir. I get that, but I guess I want to ask something else as well, because I was trying to figure out it's still stuck on the whole, the continuous time, how it would convert, and knowing that there is some sort of, what you'd say, the fault with the continuous time that they're trying to zoom in on with the Z transform here. Because as far as I understand is that discrete, so it's from minus infinity to infinity, and we're just trying to get specific points or from 0 to infinity, or 1 to or 0 to minus infinity in the Z transform, correct?
Correct.
Yes, sir. So I guess as just maybe still not clear on something. I'm not sure what it is. I probably have to do some work on that, because there's a question I want to ask, but it's just not coming.
All right, do some look it over, read it up. I'm gonna send you something else to add to this. Plus, I'm gonna send you later on over the weekend the inverse Z transform. How do you go the reverse now? In terms of concept and examples again.
Okay, sir.
Any other questions? We need more time to process it.
Yes, sir.
So those last couple of videos that you just showed, for quick reference to them, are you gonna post them on Google Classroom? Hello. Hello.
All right, it's posted already, Chad.
Oh, it is? I didn't say an update. Hold on.
This is the checkers game where grandson and granddad will bond.
All right, so we've been talking at length about the Z-transform, defining it, talking about this region of convergence, talking about how we can get the Dtft out of the Z-transform. Finally, now let's actually work through a set of examples where we'll actually get some practice at evaluating the Z-transform. So first, let's do Z-transform example 1. So in this example, we are going to find the Z-transform for the signal x of k equals this signal. So we're going to start off simple. We're going to start off with this signal that is equal to 1 at time minus 1, 3 at time equals 0, 2 at time equal 1, and a negative 1 at time k equal 2, and it's 0 everywhere else. So if I was going to plot this signal in discrete time k, it would end up looking like this. It's equal to 1 at minus 1, it's equal to 3 at time 0, 2 at time 1, and a negative 1 at time 2, and it is 0 everywhere else. What I am asked to do in this problem is I'm asked to compute the Z-transform of this signal. This is actually what we call a finite length signal, so we're actually not going to have to worry about any convergence issues here, because when we evaluate the Z-transform, there won't be an infinite number of things I'm summing up. There's only going to be 4 things that I'm summing up, because there are only 4 non-zero samples.
Did you check, Chad?
Yes, sir. Just a couple minutes ago, it's up.
Okay. All right. So that's it. One other thing that I again want to encourage you guys to do, and I can imagine the lecturer is begging you guys to do. There are a couple other things on. So we have Dtft, we have discrete time system and signal and the basic signal concept, and this is more to do with what you should have done in the earlier part of the course. Just please, guys, just watch the thing, make notes, come to the class, because that's how I know if you understand. That's how I know we don't have enough time to be going back to be discovering the things telling that this is A and this is how you shape A. We're trying to use your term of your own term of reference as to when you read and conceptualize the things or watch and understand the thing, you come to the class knowing that this is the case. What you don't understand, we will flesh them out. What you do understand, we don't have to go over them unless you want to give a brief update on what you would have learned. And that's how we kind of strengthen the thing going forward. I would always put examples / tutorial as soon as you understand the concept, so that you can get an opportunity to broaden your understanding of a particular topic. But it's pointless for me to be coming here and you do not watch or read the stuff. It then makes it very difficult. And I spend most of the period watching a video that you should have watched already, instead of working on issues and problems that you would have had with issues and aspect of the lecture. We don't necessarily want to spend the time doing that. As much as I don't mind you watching it, and you tell me that this is a part you don't understand, I would refresh it all. But again, we could do more, a bit more, if we add all white and red. Am I clear?
Yes, sir.
All right. So if there are no further questions, look out for more of the postings that are going to be in the classroom, and we will pick it up again. Listen out for Chad, because Chad is going to be communicating with you guys. The more I get on in terms of information for the class, the more I'm going to be sharing with you guys through Chad. All right?
All right, sir.
I just want to big him up in this forum, because he has been a very useful help as far as I'm concerned, and I'm sure that you guys appreciate his assistance.
All right, sir.
All right, so I'll talk to you guys again. Anything, you know my email address, shoot me an email, and I will respond. Sometime maybe not immediately, because again, one thing that I do a lot is in long meetings and sometimes travel. So I'm expected to be in another long meeting tomorrow from 10 until God knows when. Outside of that, though, I respond to your emails if there are any questions or suggestions. Okay?
Yes, sir.
All right. Have a good evening, and Chad, I'll see you for communication later on.
All right, sir.
And Miss Henry and Etal. All right.
Okay, sir. Have a good evening, sir.
You too.
Take it to the. Sure.